Okay. So I'm going to be giving a few lectures. So I thought I would first say what the theme of the lectures was, besides just something I could think of to say. So the common theme is, I'd say, moduli spaces of geometric objects. So the first talk, and then group actions on this space. So the first talk, the objects are going to be things called marked boxes, and it's going to be the modular group. The next lecture is going to be simplices and barycentric subdivision, and the group is going to be essentially SLN R. The next talk is going to be triangulations of the sphere, and I'm going to talk about Thurston's paper, shapes of polyhedra. And the space will be like, actions will be like complex hyperbolic lattices. The fourth talk is going to be spaces of polygons, and there's going to be some kind of discrete integrable system. In the fifth talk, I'm not sure what the objects are, and even what I'm going to say, but it'll be something. It might be what I'm working on now. So, okay, so today, Pappus' theorem and modular group. And this is something I did quite a long time ago. It's in the IGS publications in 1993. So first I'll give a little context. Like John said in his talk, I won't say too much because a lot of people are experts in this kind of thing. And I'll talk about Pappus' theorem. And I'll talk about the modular group. And then I'll combine them. The idea is I'm going to explain. In the end, you get some kind of. So the context is, I'd say, deformations of group representations. So. So the classic setup is you have a group gamma. And you write it like this. You have some representation into the isometry group with X. Gamma will be something like a surface group or modular group or a free group, and then possibly you have the isometry group of a larger space, and you look at you look at some kind of one or multi-parameter family of representations into the larger group, which contain zero. So, the classic case of this is where you have where X is the hyperbolic plane and Y is hyperbolic 3 space, and gamma is a surface group, and then you have the quasi-Fuchsian deformations. A more modern, or another case is where sometimes it's not always good to think of it as the isometry group of hyperbolic plane, but another example is where X is SL2 mod SO2, which is just again the hyperbolic plane, and Y is something like SLN mod SON. And the classic cases of this is where you start with some surface group acting by real projective transformations on the hyperbolic plane and preserving a circle, and you can deform so that the what's preserved is some kind of C1 convex curve. These were studied by Goldman in well, mainly by, I guess, by Bill Goldman and also by Soo-Yeon Choi. And then in the case for n larger than 3, you have the Hitchin component, which people have talked about, where instead of thinking of a conic section, you have maybe a twisted cubic in Rn, and then you can get some kind of group action on that. Another. I'm almost done with context. Another direction is, again, maybe x is H2 and y is CH2. So there you have start out where H2 is something like complex hyperbolic spaces that think of it, a model for it as the unit ball in C2. And when you intersect it with R2, you get a copy of the hyperbolic plane where the group acts by projective transformations, and then you can sometimes deform the group. So these are called complex hyperbolic quasi-15 groups. In the case when gamma is a triangle group, various people, including John and me, have studied this a lot. Then there's a general kind of family of representations called the Nosov by Laborie. And so the things I'm going to talk about, the things I'm going to talk about are kind of most closely related to these Goldman examples and to triangle groups here, and also to these things called the Nosov representations. So anyway, that's the context. So what I'm going to do now is, eventually I'm going to construct these representations of the modular group, and I'm going to start with Pappus' theorem and then go on. So I want to say a word about the projective plane, probably everybody knows this, but I'll just so it's the space of lines through the origin, or non-zero vectors mod scale. And you can identify a subset. The plane is naturally a subset of the projective plane because you take the plane z equals 1 and you just pick any point. It determines a line through the origin. And any line through the origin of non-zero slope determines a point in the plane. And all that's missing are the lines parallel to the plane. So the projective plane is a union of the plane with a circle infinity, compactification. The lines in the projective plane are all the lines in a plane through the origin, or the lines in the projective plane are just all the planes through the origin. And any line in the projective plane, if it does intersect the plane z equals 1, it does so in an ordinary line. And also there's the one line infinity. So if you're drawing, if you draw things in the plane, somehow when you're drawing lines, they really look like lines. Then there's a group of projective PGL3R is projective transformations mod scale. Invertible. So any invertible linear transformation of R3 fixes the origin and maps lines to lines. So in particular, it preserves the projective plane. It also maps planes to planes, so it preserves lines. It's a 3x3 matrix is 9-dimensional, and when you mod it by scale, you get 8. So projective group is 8-dimensional. What you can do, another way to think of it is that you can I'm going to do a good job with this. So you can map any 4 general position points to any other 4 general position points in a unique way. And I guess this is how maybe how painters did perspective. The fact that lines go to lines mean that at this point it has to go to this point, and then these two lines meet at infinity, and so the point at infinity has to map here, and so on like this. So a map of this big square to this quadrilateral, it has to map each of these squares to those quadrilaterals, and then you can keep subdividing, and this will determine the map. You could paint, because if you had some kind of a face, you could see where it intersected these squares, and you could transplant it over here. So you would draw in perspective. Okay. There's another. Maybe I'll just. There's another space which is just R2 dual. This is the space of lines. In RP2, so in other words, it's a space of lines through the. You could think of it as a space of two planes through the origin in R3. And there's certainly some special maps from RP2 to RP2 dual. For example, you could use the standard inner product on R3, take any line through the origin and map it to its perpendicular plane. So that special map induced by the dot product, it preserves incidence relations. So if you have some number of collinear points, they'll map to some number of coincident lines. And in general, what a duality is in general, it's a composition of that particular map with a projective transformation. Or put another way, a duality is a map from the projective plane to the dual, which preserves incidence relations. So it turns out that every one of them is just given by composition of the inner product map with some projective transformation. There's another one that's nice to look at, which is that if you fix the unit circle, then if you have a line that intersects the unit circle, then you can, you can say it like this. You take a map on the outside of the unit circle and map it to this line. So that this is also a duality, and rather than given by the dot product, it's given by the standard Lorentz inner product. If you look at this in the projective plane, this is a projectivization of the light cone. If you want to know what the ordinary dot product is, you do this map and then rotate 180 degrees around the center of the circle. Okay, so that's some things about the projective plane. One more thing I want to say is that there's one more space I want to look at, which is the flag space. And this is the set of pairs, EL, where P is in RP2 and L is in RP2. And P is a point in L. So the flag space is a three-dimensional space. It's a circle bundle over the projective plane. It's also a circle bundle over the dual projective plane. Because once you fix a point, there's just a circle's worth of lines that go through it. Once you fix a line, there's a circle's worth of points on the line. The other thing, I'm using R here, but everything I say could be done over any field except characteristic 2. So anyway, it's just easier to draw pictures in R, but somehow a lot of what I say, it just works in any field, and then there are just certain moments where you need R. Okay, any questions so far?
Except over any field, then you have non-trivial automorphisms.
Yeah, that's true. Yeah, that's true. There, if you have some other fields, you would have other automorphisms, which, who knows what it means.
No, in the sense that, yeah, okay.
Right, right.
Which three-manifold is the flag space?
Which is it? I mean, it's a finite quotient of the free sphere. I think it's the free sphere mod. I want to say a group of order 8. Yeah. Yeah. But,
Is it the quaternion? Yeah, probably.
probably. Yeah, probably. I'm not sure which it is. Okay, so Pappus' theorem. So what it says is, you have 3 lines, 3 points on a pair of lines. Say, and then you connect the points up like this. And then the theorem says that these 3 points go through a line.
So here we're in projective planes.
Yeah. So this is in RP2. But again, the theorem is true over any field as long as the field has characteristic not equal to 2. The reason why you want characteristic not equal to 2 is because you want to be able to put maybe any field except Z mod 2. You have to be able to put 3 points on a line to do this theorem. The other thing about Pappus' theorem is that it's a self-dual theorem. Like anytime you have a theorem in projective geometry, you can apply a duality to it, and then you'll get some other statement where everything involving the word points is switched with everything involving the word lines, and vice versa. So you might wonder, like, what theorem do you get if you sort of dualize Pappus' theorem? Pappus' theorem looks sort of like there's 6 points and 2 lines, so it doesn't really look like, it looks like you might get something different. But in fact, you can equally well think of it as being given by, you can equally well specify the data for Pappus' theorem by specifying 3 lines through a point and 3 points through a line. So in fact, if you were to trace through what you get the same theorem back again. It's a self-dual theorem. That's going to be important later. Okay, so I guess I have a little bit of time. I mean, I'm not going to prove it, but there's an interesting theorem. If you have a grid of points, so suppose you have 9 points in the projective plane on 3 lines, and suppose you have some kind of cubic curve. So imagine you have a cubic curve which contains 8 of the 9 points on a grid, and it also contains the 9th. This is known as it's a case of what's called the Cayley-Bacharach theorem. And if you specialize this to where the cubic is like 3 lines, there's the product of 3 linear functions, then it implies Pappus' theorem. There's also, I guess, Pascal's theorem where you put 3 points on a conic and you do this thing. Okay. So somehow the result, this is called Pascal's theorem, this is called Pappus' theorem, and then this general thing implies both of them. And this is basically proved by dimension counting. I won't do it, but you look at the vector space of all cubics and you just check that it works. Okay, Pappus' theorem. So now I'm going to make a chart which is going to explain kind of the philosophy behind the rest of the talk. So on the one hand, there's, maybe here I'll write Pappus' theorem. And what I'm going to write over here is theory addition. So it turns out that Pappus' theorem is really, you could say it's a deformation of Ferry addition. Ferry addition is the wrong way to add fractions. So I'm going to try to convince you that Pappus's theorem is the natural deformation of Ferry addition. And Ferry addition relates, of course, to the modular group. And so you could ask, like, what relates to the modular group in the same way that Pappus's theorem relates to Ferry addition? And the answer is what I'm going to talk about, these representations. So it's kind of a natural construction. I'm going to try to convince you that Pappus's theorem is quite related to Ferry addition. Okay. All right. So okay, the modular group, this crowd, it needs no introduction. PSL2Z. So Ferry addition is and usually what you do this when A, B, C, and D are a matrix of determinant plus or minus 1. If you did fractions like this way in elementary school, you wouldn't be here today. Okay, so you add these two and you get 1 over 2, and then you join them by semicircles, also known as hyperbolic geodesics. You Ferry to add these two and you get 1/3, 2/3, etc. And then you take this picture and you just translate it by integers, and this gives you the usual Ferry triangulation of the hyperbolic plane, and the modular group preserves this pattern. So let me show you how this is related to Pappus's theorem. So what you can do is you can on top of this picture you can superimpose a square of side length 1 and center it at 1/2. And then you can put 6 points like this as the starting point for Pappus's theorem. Then you can do Pappus's theorem. So
what is the height?
this height is 1/2. This is 1/2. This is 1/2, and this is 1/2. In fact,
it touches the circle.
yeah, that's right. It would actually touch the circle. Yeah.
Sorry.
You're good. It does actually touch the circle. In fact, the height isn't important for this. It turns out that it doesn't matter what the height is. It could be 1 or 1/2 plus epsilon. It doesn't matter. Just as long as it's a rectangle with the same amount above and below. So now you do Pappus's theorem. And sure enough, the point you reach is the Ferry sum of the two endpoints. And now you can repeat the construction. You can go on this side and do Pappus's theorem again. And sure enough, the point you get is the Ferry sum of the two endpoints. So if you keep iterating this construction, you will, this is a kind of a geometric construction of the usual, I think this is, some people call this the Stern-Brockott process for generating these fractions. But anyway, this process of recursively generating these fractions using Ferry addition is gotten by taking this particular initial choice of Pappus's theorem and then just taking the conditions and iterating them over and over again. So that's why Pappus's theorem, at least for this particular configuration, is Faraday addition in disguise.
So you get a third line and then you iterate.
Yes,
You start with 2 lines, then you get a third, and then you iterate
yes,
the middle ones.
yeah, that's right. So you start, that's right. So what I did in this construction is I started with these initial conditions here. And then I got this here, and I used, it's just like for Faraday addition. You start with 2 fractions and you Faraday subdivide, and then you take one and the one you just got and you repeat. And this is a way of generating fractions on the line. But if you do it geometrically with this, starting with this particular square, you will produce exactly the same fractions. So I mean, I'll explain why this is true later. but anyway, it's this is sort of a construction of this Faraday addition. But what's nice about this is that you can deform this construction rather than start with a particular square. You could slide the points up and the middle points up and down. You do this for other points, and you'll get some other kind of thing. That's what I'm going to talk about. So make sense so far? Basic operation. Okay, so I want to say a little bit more. Sometimes I won't draw the upper half plane. I'll just draw the unit disk, and I'll draw the Faraday graph like this. So I want to talk about, before moving on to, I want to say a little bit more about the modular group. I want to explain why I want to talk about 2 commuting modular group actions on a certain graph or a certain set. So my set is going to be the directed edges in the Faraday graph. So an element of my set is an edge of the Faraday graph in some direction. So for each edge, there's 2 possible directions. So I'm going to describe an action on this set. So firstly, there's an element I, and it's just switched the orientation. So I, given any oriented edge, you switch the orientation. What's T? So then there's an operation T. What T does, I'll draw it like this. T takes an oriented edge and it rotates it one click clockwise about its tail point. So this is T. And then there's B. So this is some edge, say X, and this is T of X, and this is now X, and this is, maybe I'll call this X prime, and this is 2X prime. So these are these 3 operations.
B of X.
I'm sorry, B. Yeah. So I, T, and B, they generate a group action on this set. The question is, what is it? And there are some things you can check. Well, certainly I squared is the identity. It turns out that TIT is B, and BIB is T, and TI, BI is the identity, and BI, TI is the identity. So these are things to check. I'm not going to embarrass myself doing this, but it happens. Like if you do T and then you switch it, so here's T, and then now I'll switch it to I, and then I'll do T again, and it goes up here, and so that's B. So that's a quick proof that TIT is B and BIB is T is similar, and these 2 are similar to that. So if you set something like alpha equals I, beta equals, say, bi or something, then beta cubed is bi b I bi, which is bi ti, which is the identity. So alpha squared is the identity, and beta cubed is the identity, and that's almost enough to check that this is the group is in fact the modular group. I mean, it acts transitive. Well, it's not any kind of group of isometries of the hyperbolic plane. It just acts on the set of these directed edges. I guess it's like if you have the Cayley graph of a group, there's a left action of the group on the Cayley graph, and then there's a right action which just kind of permutes the edges. So I mean, so there's kind of a geometric action on the left and a combinatorial action on the right. So there's the ITB action. It acts transitively on these directed edges, and then there's the usual modular group action acting by hyperbolic isometries, which also acts on the directed edges. So you have these two modular group actions, and they commute, because if I do any of these operations and I apply an isometry, it's the same as applying an isometry and doing the operations. So anyway, that's what you get from the modular group. You get actually two commuting actions of the modular group on the directed edges of the fairy graph. Okay, so So the next line in this little dictionary is the directed edge of the fairy graph. And on the right side, there's going to be something called a marked box. And so what I'm going to get is just like for the modular group, you get two commuting groups of group actions on the set of directed edges of the fairy graph. I'm going to get two commuting group actions of the modular group on the space of marked boxes. So the next plan is to describe the operations I, T, and B on a marked box. Okay, so so informally speaking, a marked box is just the data for an application of Pappus's theorem. That's all it is. So you could think of it as a marked box as just 6 points, 3 of them collinear, but it's probably best to think of it as it's really 6 points and 6 lines, which have this incidence relation between them. But informally, the way I think of a marked box is it's just a square with a top point and a bottom point on it. So the idea is that one of these marked boxes is just determined by the 2 lines and the 6 points. And if you're interested in this up to projective transformation, you can move any 4 general position points to any other 4. So you might as well move the outer 4 points to the vertices of the square, and then the inner 2 points would be somewhere on this line. If it looks like this, the box is called convex. So in other words, these 2 points, if they're on the inside of the square, on the top and bottom edge, they're convex. It's convex.
So that's a picture where I wonder about the inside and the outside.
Okay, so well, okay, so you can say this in a projective way. Like the idea is that these 2 lines intersect at some point. In this case, it's a point at infinity. And then you can look at and so what I mean by convex is that if you look at this point and the infinite point, they separate the other 2 points on R. So I mean, in order to do this, in order to make this definition, you have to have an ordered field. So like this definition wouldn't make sense on, you know,
Okay, so that's you use the orientation of the circle somehow.
yeah, you use the fact that the lines are circles. I mean, if the lines weren't,
Okay, yeah.
yeah, I mean, if it was in C, it doesn't work.
So you can do it over any ordered field.
Yeah,
What's the config? Could you draw the configuration corresponding to a non-convex Markbox?
sure.
You just choose another set of
I guess
your
I
four
took
points.
it when he said that.
There.
The,
There.
yeah,
That's what
but
I'm saying.
I thought you said both satisfied the word instance.
It would.
It still
I mean-
satisfies by instance relation, doesn't it?
Oh, well, I'd have to draw, yeah, so here's, yeah, I mean, so here, so let me label everything. So this is like A1, A2, A3, B1, B2, B3, and this is like A1, A2.
So when you said they satisfy certain instance relation, it didn't implicitly assume that A2 was between A1 and A3.
No, that's right. It's just that this line connects A2 to B1 and this line connects B2 to A3. So you could draw those lines here with the same instructions. Yeah, in terms of describing, so formally speaking, I mean, yeah, I tried reading this last night and I decided to define an overmarked box as a 12 tuple of things, 6 points and 6 lines with certain incidence relations, and then you want to, mod out by some involution, and a marked box is some list of points and lines with some incidence instructions. Which I'm not going to do. But look, basically what you do is you draw a square,
Yeah, sure.
and you pick a point on the
I
inside.
understood that picture, I just didn't understand.
Yeah. The reason why you want to do this, the reason why you might want to do this is because later I'm going to talk about how dualities come into the picture. So at some point, you want to have somehow a symmetric description. And also you might want to describe this as like some subset of the flag space. Some finite points in the flag space. Okay, so what are the operations? I have to describe I, T, and B. And I'm only going to describe it for these convex boxes. Yeah, so box comes at the top and the bottom. So here's a box. Maybe I'll call it X. So these convex boxes also have a convex interior. What's a convex set in the projective plane? It's one way to say it is that you can move it by a projective transformation so that it's a convex set in the affine plane. Another way to say it is that it's given by a convex cone when you look at it in R3. Okay, so this is so this is I of X. I of X is that you switch the top and the bottom, and then you so it's just the same 6 points, but they're taken in a different order so that this is the convex set that's selected. So I squared is the identity. If you think about on top of a marked box, if you think about just combinatorially as having sort of an edge just directed from the top to the bottom, then just like with the fairy graph, I has the operation of switching the orientation of the edge. So does it make sense? Okay. Then there's T and B. So the operation T is doing, you do Pappus's theorem, and then you take, it divides into two halves, and T is the top. And then B of x is the bottom. So combinatorially, if you think of edges connecting these kind of points in the middle, I and T do the same thing combinatorially as what's happening on the Fairy graph. In fact, if you start with the kind of standard marked box where they're like this, then you can identify each marked box with one of these directed hyperbolic geodesics. And then in this standard picture, I, T, and B do exactly the same thing as what Fairy addition does. And what is I? It's just inversion, or it's just turning. I is turning all the directions around. So at least for the standard marked box, I, T, and B have exactly the set of this group of operations on marked boxes generated by I, T, and B is a modular group. And you can just see it directly for this picture because it's just isomorphic to what you do for the directed Fairy graph. But then when you deform, nothing much changes combinatorially. So you get a modular group action on the space of marked boxes. Does that make sense? Okay, so I've now described one modular group action on the space of marked boxes. And now I want to describe something which is more like all these other, more like quasi-Fuchsian groups. I want to talk about an actual group of transformations. So I want to talk about the symmetries of this construction. So there's two ways to think about it, and I'm going to explain it first just in a purely computational way. How I guess I'll say how I discovered this. I mean, a marked box, there's two parameters you can associate to a marked box. I mean, you just move it so that the outer vertices are the vertices of the unit square, and then you just see how far over the two inner points are. So there's a two-parameter family of marked boxes up to projective transformation, and they have these parameters. So you can start performing these operations, I, T, and B, and you can ask just experimentally, like, what happens to the parameters? Do they change as you do this? And it turns out that when you look at the parameters that you get, you only see two different kinds of marked boxes in an orbit. So that suggests that there's a lot of symmetry, because if you have two marked boxes with the same parameters, then there's a projective transformation that takes one to the other. You just map the outer points to the outer points, and then the inner ones, by definition, go to the right place. So there's a lemma, and it's that there's two lemmas. The first lemma is that there exists, for all marked boxes X, there exists a projective transformation, say T, with the action so just in terms of the picture, there's T of x, B of x, and then I of x is kind of going around the outside. In the projective plane, these things make a kind of a loop, and then there's a kind of a T that just kind of shifts this around. One proof of this fact is, well, you could do it computationally. You could just compute the invariants and see that they were all the same. So then there's a projective transformation that takes T to B, and you can just trace where the lines go, and you can see that B goes to I and I goes to T. So there is a completely computational proof. There's also a way to see it geometrically, which I'm going to attempt to do. You start by drawing an equilateral triangle, and then you extend the lines. You could draw a picture with threefold rotational symmetry, so that when you take these three, I've drawn a bad picture, I think. If it's really true that there's a projective transformation of order 3 that permutes these three boxes, you should be able to change the picture by a projective transformation so that the thing is a rotation of order 3. So I was attempting to draw that. The start of it is easy to draw. You just you put points like this, and then you draw the inner to the outer in all cases. Like so, you call this like so. So this is one of the marked boxes, and then the other three are, there's one over here and one over here. So this is like I of x, and this one is like T of x, and then this one is like B of x. And you can check that there's a 2-parameter family of pictures like this. This is a theorem in projective geometry, configuration theorem that this holds, which expressed, you could say that this construction has threefold projective symmetry. That's the content of this configuration theorem. Anyway, but maybe it was better just to say it's a calculation. But the point is that if you go back to the fairy graph, for any, IT and B, they're just, you take a triangle in the tiling, and IT and B just all go around in the same direction. So the hyperbolic geometry statement is that there is a hyperbolic isometry that just permutes the three sides of a hyperbolic triangle cyclically. So what I'm saying is that the Pappus construction has the same symmetry for all marked boxes, and if you do it for a standard marked box, you're just repeating the fact that a hyperbolic triangle has threefold hyperbolic symmetry. So this already says that this is the group of projective symmetries of this thing is big, because somehow for every marked box you can take I, T, and B, and you get this order 3 projective transformation. So the modular group is Z mod 2, free product Z mod 3. So where's the Z mod 2? Well, you'd like to just say that here, what else do we have in the modular group? We have each edge in the fairy graph has a natural center, and then there's a hyperbolic isometry of order 2, which just rotates around that center point and preserves the edge. So we'd like to see that there's a projective transformation that maps. Yeah.
Sorry, I'm really worried now talking about hyperbolic isometries, but before you were very careful to point out that the right action of PGL2Z on this thing is different from the left action.
Yes, okay, but these left and right actions happen to do the same thing to this particular edge. The element I in the combinatorial action reverses the orientations of all the edges while preserving each underlying edge separately, whereas the hyperbolic isometry
Right.
reverses the rotation of this
So
edge.
when you wanted to do that, what you actually wanted to do was to dualize, do the hyperbolic isometry and dualize back or something like that. Is that what you're?
No, I just want to do the hyperbolic isometry. I just want to put my finger at this point and rotate the hyperbolic plane around it. So that's a different action because, like, for example, this edge will map to this edge.
I agree it's different, yes, that's what's concerning. Anyway.
That's what I said. There's two modular group actions on the.
Well, we talking about the left one or the right one? Because I thought I and B were all on the right.
Okay, I and B are all on the right.
Yeah.
And now we're talking about the left.
This
action.
one's the left one.
This is on the left.
Oh, this big T is in the left.
Right. So what I did was, okay, so let's see. So on the right, I described these combinatorial things, I, T, and B.
Yeah.
And now on the left, I'm sort of making my way through the analogous things.
Okay.
And what I've done so far is I've described this rotation by order 3.
Yeah. I'm
Yeah.
sorry for.
And now I'm going to describe the rotation of order 2. So I have to describe a projective transformations. Unfortunately, there is no projective transformation which does this. So there's a second lemma, and this is the moment where lemma 2 for all marked boxes X, there exists a duality with action X goes to IX goes to X. So this can also be proved computationally because you can start with a marked box and take the dual marked box and you can check. I mean, it's if you identify the right cross ratios, you can verify that this is true. But I'll just again draw another one of these pictures, which probably isn't any better. So I want to try to draw a marked box in such a way that it looks like it's dual, or it looks like I of it, or it looks dual to I of it. It took me a long time to get this straight. So here's the picture. So I've moved the picture by a projective transformation so that the central points are points at infinity, 2 points on the line at infinity in the projective plane. T is out this way and B is out this way. And these are, so there should be 12 things here. There's 6 points, 1, the origin's not, this, and then this, that's 3, this, and then that's 3 more. Then there's these 3 lines, and there's these 3 lines. And these 3 lines all go through the 1 point, and these 3 lines all go through the 1 point over there. So this is a picture of a marked box in all its glory with the 6 points and the 6 lines. And if you, the fact that the, if this is the point P and I do this, what's the standard inner product? If I go to this point and then I rotate over to here. Anyway, if you do the standard inner product, it maps this point to this line, 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 and reverse. It's you might wonder, is it an automorphism of the marked box? And almost, it's an automorphism with some relabeling. When you check what the relabeling is, you see that it's the standard inner product maps the marked box to I of the marked box. So that's a geometrical way to see this. But it might be better just to say modular calculation. But anyways, but combinatorially, now I've described an action of, well, for every directed edge, I get an element of order 2, and for every triangle, I get an element of order 3. And at least in the standard case, this is exactly the left-hand modular group action. And as you start deforming the marked box, you're producing a 2-parameter family of deformations of this action. So where does it live? It doesn't live in the Lie group of projective transformations. It lives in the Lie group of automorphisms of the flag variety. I mean, it's because projective transformations, I mean, both so the idea is that if you have a duality, if delta is a map from RP2 to RP2 dual, then delta acts on the flag variety, because delta PL is just delta of L, delta of P. In other words, delta maps points to lines and lines to points. So these are analytic diffeomorphisms of the 3-dimensional space. So you start with your marked box, and here's S and here's T, and you vary these numbers and you get different representations of the modular group. And okay, so
Is it really a semi-direct product that way around? It seems.
okay,
It
it's
sounds PGL3R.
let me. I don't want to answer that now.
It's a duality and switch.
Right, so that should act on.
Yeah, let me just leave it like that.
It should act on PGL3.
Yeah, let me just leave it like that. It's the group of automorphisms of the flag variety.
Yeah, but wait.
Right.
With what structure? I mean, if you see the group of automorphisms of the flag variety, then
Well, so it's
the
definitely
structure-
okay. So it has a subgroup of order 2 of index 2, which is just the projective group.
So I had to do the other way around. Yeah.
Okay. Okay. So yeah. So it's probably yeah. Okay, let me just leave it down. It is a subgroup of index 2. That's the PGL3R.
Just a group of automorphisms as a building, but you allow the swapping of networks.
Sounds good.
Okay. Yeah, I mean, there's a particular element of order 2, which is nice, which is just the duality coming from the standard dot product, and then you can just see what that does to projective transformations. Okay, but I hope it's clear what. So the idea is that in the case of the modular group, you have this combinatorial action, and then you have the usual modular group that we know and love, and then here. The combinatorial action is these operations on boxes, which come from Pappus's theorem, and then you look at the projective symmetries of an orbit, and that gives you the representation. And then there's 2 parameters. So this is a 2-parameter family of deformations. So what I want to show you now is that for convex marked boxes, these representations are discrete groups. They have a domain of discontinuity in the flag space, and the quotient is the trefoil not complement. That's the punchline. What are they? There's a paper, I guess it's a paper in 2017 by Barbeau, Lee, and Valerio, where they show that these representations are the limits of anosov representations. So these are not what are called anosov. If you don't know what anosov representation is, you won't care at all about this. If you do, then maybe you'd like to know that Misha Kabovich told me that these representations are relatively Anosov in his scheme of things. So if you know about Anosov representations, then the constructions I'm going to do next are going to look familiar from Anosov representations. If you don't, then just go with the construction. Okay, so we're on. So I want to try to show that these are discrete groups. I want to identify their limit set, domain of discontinuity, and then I'll stop. Okay. All right. So
So you mean it's the limit of Anosov in the same way that the natural realization of SL2Z is the limit of it?
yeah, that's right. You open. Okay, so there's more to this kind of translation. I mean, you can open up the cusps a little bit and look at groups with Cantor set, limit set. Well, it turns out you can do this in projective geometry as well, according to this paper, this new paper. So Valerio had written some precursors in her thesis a couple of years ago, where she had got the index 2 subgroup where you forget about the dualities, but then these guys figured out how to get the whole thing. Okay, so actually the other thing about this is that if you don't know about this, this sort of has a lot of the features of the Anosov groups in a natural way. So like you start with a marked box, and there are some 2 points of interest to you, and then you do the construction. All right. Yeah, you go away from the paper for a while. You can't remember the details. Okay, so anyway, so now you have three special points. There's combinatorially there's an identification of each marked box with a directed edge in the fairy graph, and if 2 of these directed edges share an endpoint, the corresponding marked boxes also share a common endpoint. So like if I just always use this edge, I'm getting all the marked boxes which share this point. So there's a map from the circle, at least the rational points from the circle, into well, I'm going to say this nicely. It's the flag space, because not only you pick the endpoint of one of these geodesics and you map it to this point, and what line do you use? You use the line that's the top of the box. So this is a map from a dense subset of the circle into the. It's really a pair of maps. One is a map into the projective plane, and the other one's a map into the dual projective plane, just like with the Anosov groups. And so the one point is contained in the one line. So this is a map from a dense subset of the circle into the flag space. And if there's any justice in the world, this should extend continuously. So let me try to explain to you why this map on a dense set extends to be continuous. The basic idea.
Somehow, if you were going from the circle, you wouldn't know where the other 2 points, corners of your box were. You're just knowing about flags. You've got slightly more data there, haven't you? Because I could go from that same point to the same flag, but choose different corners to my box.
Oh yeah. The center point is, for these convex marked boxes, the center point is distinguished.
Oh, okay.
Yeah, you could do that, but you wouldn't want to do that.
Okay.
The reason why you wouldn't do that is because then it wouldn't extend continuously. So the reason why this works, the basic reason this works is that the as you iterate this construction, the boxes are getting small, and you can kind of draw something like talk. Every picture is the same. Sorry about that. But there's this diamond here, And then there's another diamond here, and there's a diamond here, and so on, like that. And the, at least on the, just for the points anyway, these points go to the endpoints of these diamonds. And you just need to see that all of the diamonds, the nested intersections of these diamonds shrink to a point, to points. And once you have that, the map extends continuously, at least on some segment. And then if you want to get the other half, you just apply the I map. So to prove that this thing extends continuously, you just need to show that all these diamonds shrink to points. And then just by symmetry, the whole map extends. So the basic idea is, I mean, I'm not going to go through the proof of the whole thing, but like there's two things that are going on. The boxes are getting smaller and they're getting thinner. So, I mean, so I guess there's no doubt that they're getting smaller. And how do you analyze this? Well, suppose you have a really long word in the modular group. Then one possibility is that it happens often that this gives you a nested sequence of these boxes. And one thing could happen is that the nested sequence is detached infinitely often. It happens quite often that each successive box is totally disjoint from the one above it. And then you have a situation where you have some kind of convex set, and you have some smaller convex set inside. And modular projective transformations, there's only one picture, basically. And so the inner one gets smaller by a definite amount. Like they couldn't be limiting down to something like this, because then the Hilbert diameter of the inner one inside the outer one, you can put a Hilbert metric on any convex set. The Hilbert diameter of the inner one, Hilbert diameter of the distance between 2 points is you take a line joining them, you take the log of the cross ratio of the endpoints. So if you have some picture like this, you have some cross ratio which is going to infinity. But modular projective transformations, there's only 1 or 2 pictures you see, and so this can't happen, so the thing has to shrink to a point.
I'm confused about one thing. So do you ever apply T inverse? You said they're nested, so you look at
Oh,
T
well, I first deal with just an arc on the boundary, and I just check everything in here. And then if I'm interested in some other arc on the boundary, then I mean the whole thing is invariant under projective transformations. So really all I need to show is that the map extends continuously on some segment in the boundary. Because the group you can map any segment over any other segment. So I don't really need to analyze everything. I just need to analyze what happens inside a particular box. So what I'm saying is that if you look at the nested intersection of boxes, unless you have some long word which is like parabolic, like always fixing the same edge, then the boxes shrink to 0 in diameter. And so even more strongly, these diamonds shrink to 0 in diameter. If the boxes are all sort of going along the top, then they're not shrinking. They're kind of converging to a line segment, but the diamond is shrinking to a point as well. So in all cases, these diamonds are shrinking to points and it extends continuously. The other thing that's happening is that they're getting thin. Like, what's the angle of the box? Just in the Euclidean plane, same picture. The angle is just this angle. And so when you apply the construction, the new angle is smaller. And again, it's a definite amount smaller. So what I'm trying to tell you is that
Is that angles not a projective from there?
well, you just for the purposes of analysis, you just look at what happens inside one marked box, and you just move it to be the largest one to be the square. And you use the Euclidean metric for angles. And I mean, or if you like, you could put some Riemannian metric on the projective plane at small scales, they're comparable. But what I'm saying is, imagine you have a big marked box and a small marked box. So that the projective transformation that maps the big one to the small one, firstly, it contracts distances quite a bit, but also it kind of squeezes angles quite a bit. So these two features of contracting distances and squeezing angles together are what's going to let you analyze the domain of discontinuity. Okay, so, okay. So, I'm not gonna, maybe I'll go, I wonder how long this is gonna go on, so maybe I'll go till 2:30. 3:30. Okay, so, you know, this map, you can use things about it to get information. Like so now what you have is you have this kind of, in general, it's some kind of fractal curve, and there's a fractal line field. There's this kind of continuous curve, and there's a continuous line field, and because
this picture is in the flag manifold.
yeah, this isn't a flag manifold. I mean, you could draw it in the projective plane, but you can, I mean, that you can, you know, if you can think of it as a curve in a line field, or you can just think of it as a curve of flags.
Can you characterize this topologically? I mean, whenever you have something like that, can always obtain flags continuously.
Oh, you mean for these or
Yeah, I
something?
mean, can you say the class of things obtained with this procedure is the same as the class of, say, continuous?
No, I think, I mean, oh, I see. You could say like, I mean, suppose you look at like a curve and line field with modular symmetry.
And prove that on the separate properties you always obtain.
Yeah, I didn't try to do that, but my guess is that's probably true. Like this is, all, I mean, all you can get. Maybe, I'll just say this: that each line intersects the curve. Each line intersects the curve exactly once. That's pretty neat. And it's the unique.
So that doesn't really make it fractal. I think.
But you could say, is there another continuous line field that also intersects the curve only once? And the answer is no. This is the unique line field that intersects the curve exactly once. And given the line field, there's a unique curve that intersects the line field at each point exactly once.
When you say fractal, it's indeed
Okay, so Anna Wienhardt, student, did she had a master's student that did some experiments where she was trying to compute the box dimension of these sets. Okay, it's a fractal except in one case. In the standard case, it's just a real line. And it looks like this. So the student computed the box dimension by, I'm not totally convinced by his calculations, but the dimension seems to get up to about 1.3 or something.
So what is the box? Can you remind me?
So the box dimension of a set in the plane is you have some set and you subdivide the plane into squares. The side length 1 over n. And then about n to the d squares will intersect your set. And then d is the box dimension. I mean, you have to, take limb soup and so on if you want to. So anyway, so you could do this experimentally. You can count the number of boxes, and this guy did this for n up to about a million or something. I don't know how much, but the dimension seems to be greater than 1. This is an open question. I don't know. I mean, there's this great result of Rufus Bowen's where if you have the dimension of a if you have a quasi-Fuchsian group, then the Hausdorff dimensional limit set is bigger than 1 unless it's Fuchsian. This was the first of many theorems about these limit sets, and so.
So what about the Hausdorff dimension?
It should be the same.
It should be the same.
Yeah, I mean, there's lots of dimensions. I mean, I just picked the box. This is the easiest one to do on the computer. So
So there will be a line field which is invariant on the group.
Yeah, so what does the group do? The group, there's an index 2 subgroup which preserves the curve and preserves the line field separately. And then there's this order 2 element which switches the curve and the line field. So anything you prove about the curve, like that it's continuous, implies that the line field is continuous as well. So this is exactly the setup for an groups, except like so it's also true, like if you have a hyperbolic element, it tends to contract around the fixed point, but it also has unequal eigenvalues, like you want for an anosov group. So it's almost an anosov. The only reason it's not an anosov is because you have these parabolic elements. So,
This is okay. That makes the line field possible. So
it makes it what?
the existence of the line field possible because you have parabolic elements somehow.
Yeah,
I mean,
yeah, right.
That's not really-
Right, right, the line field is, right, it's the closure, yeah. Yeah, the line field is it's the closure of the fixed lines of the parabolic elements.
Right.
But it's also the closure of the, like expanding lines of the hyperbolic elements or something. So it has several definitions. Okay, so, maybe I'll just go
Why?
on.
Just because invariant line fields suggest Sullivan's sphere. I mean, I don't know if these analogies.
Oh, yeah, that's a little different, I think.
Yeah.
Right, because there you have like line fields which come from like the deformation of the group or something. This is more like this is more like with anosov groups. Well, like with the Hitchin component, you have like the curve and then the tangent line.
Okay, yeah.
It's more like that.
Right.
So maybe I'll just say this and then stop because I've talked long enough. You have you have maybe the curve. So lambda is the curve, and then L is the line field, and then you have this kind of lambda L. Is the curve of flags. So there's two natural surfaces that you can make, and I think this is also like this theory of Kapovich and Lee and Porty. You can fix a point on the curve. And you can look at all the lines that go through that point. That's not in this curve, but that's a surface. And I guess that's a torus because it's a circle over a circle. So you have this, you have a rule of torus gotten by, it's all the flags where P's on the curve. And then there's another torus where it's all the flags where you take, where the line is from the line field and the point is on the line. So you have this kind of picture of these two ruled tori. It's hard to draw this. And these two ruled tori intersect along a curve. And what I want to say is that the complement of these two tori is the domain of discontinuity. And the quotient of the domain of when you look in the standard case, you can identify this domain of discontinuity with the tangent bundle to the hyperbolic plane, and the quotient in the standard case is the Dreffelon complement, and when you deform the group, nothing changes topologically. Well, I'm getting mindful that this is going on a long time, so maybe I'll just say that. The limit set is these complement. The limit set is the union of these two tori. So the domain of discontinuity is the set of flags where the point's not in the curve and the line's not in the line field. Right. Okay, so I guess I'll stop.
So this is kind of a picture which you, I mean, you can do over any real field. So, I mean,
Yeah, I never.
so you can do it over Robinson fields.
Certainly.
So that means,
Yeah, if you wanted to.
so that means that stuff survives when you take
Yeah,
control limits of these representations.
I guess so. I
So
mean,
that-
right, you could do, right.
The fact that you can describe it by just using the ordering of R
Yeah.
tells you something about
Yeah.
the omega limits of these guys.
Yeah, I mean, I always was wondering, like, what the action is like on the symmetric space. I guess this is what people are wondering about for various kinds of. I mean, I'm describing everything as an action on a three-dimensional flag space, but there's also, it also acts on these dualities also act on the five-dimensional symmetric space SL3 mod SO3. And I've always wondered, like, I always imagined, I thought there'd be like some kind of pleated surface that would sort of go out to this part of the boundary, but I never figured it out. Right, or you could do it over these other fields, like in Paul's talk, where he was doing all of this stuff, the modular group over fields and characteristic P. So you could also deform everything he said. Right. It's a completely natural construction of fields.
The dimension depends on S and T.
Yeah, right. I mean, in some mysterious way, I mean, like, I was never able to prove that the dimension is bigger than 1 for any parameter.
Yeah, because that is something which doesn't make it the same than I mean, for Anosov you have these curves are C1.
Yeah, like for the hitching component, there's C1.
Yeah, for the each.
Yeah, maybe this is part of the Barbeau component or something. There's a name. So there was a paper of Kurt McMullen's on self-affine carpets, where you kind of take Sierpinski carpets, but they're kind of self-affine rather than self-similar. He was able to compute the dimension of these things based on the combinatorics. And I mean, a projective transformation is really basically an affine transformation on small scales, in the same way that a Mobius transformation is a similarity on small scales. So it's possible that some techniques like that could show the dimension is bigger than, or maybe the dimension's 1. I don't know. I don't completely trust these numerical experiments. I mean, it's a little tricky. I mean, the usual methods for showing that the Hausdorff dimension is bigger than 1 don't work for this. So it's on the boundary of what people know how to do. It's like a limit set in a higher rank group. It's, I think maybe if you were trying to compute the limit sets in higher rank groups, this would be the first one you would try to do. Right. Or it's, you could compute a Poincare series or something. I don't know. All right, so.
Yeah, right, but there, yeah, okay. Wait, but there, yeah. It's not clear anymore, there's a relation.
Yeah.
Between the Hausdorff,
Oh, between the Hausdorff dimension and the Poincare series.
there's no.
Yeah.
And there's probably none in the sense that for Hitchin representations, if you go away from the function locus,
You said it goes down.
Yeah, it
You're
goes
saying-
down.
Yeah, that's funny.
it goes down, but the limit set is always rectified.
Yeah, the limit set's always one dimensional.
It's
Yeah.
C1.
Right, C1 in fact. Yeah, these are,
So
yeah, these things, the limit sets, you know what they look like? They look like graphs of the stock market somehow. It's really true. Like one time I was looking in the paper and I looked at like some graph of the stock market over a long time and I said, what? That's the picture I drew of this limit set. And I guess what's going on is that there's some kind of like non-similarity scaling if you take a graph of the stock market over a long time. You know, it's like a random walk. There's some excursion times are not linear. And so if you take the graph of a random walk and you rescale it by a long way, you'll see a very spiky kind of graph. There's some, it wasn't totally crazy, but I thought this picture in the newspaper looked exactly like the limit sets. Yeah, the limit set on very small scales, it's extremely spiky, which is it's kind of amazing that there's this unique transverse line field. That's something which is kind of amazing to me. At first I thought it meant, I don't know what to make of it. At first I thought it meant it had to have dimension 1 because it has a transverse line field. But
well, but you need, okay, so you say you prove there is a unique transverse
yeah,
line field.
yeah, I proved it's unique, except in the standard
Yeah,
case.
that makes it very non-differentiable, because if you have something which admits tangent, then you have tons of
Yes, that's
transverse
right.
line
No, I
fields.
know. That's right. It's right. It doesn't even have locally. There's only one. It's locally unique even.
Right, so it's not C1.
Right. No. It's super spiky. But it could be. Maybe it's so spiky. It's. You know where do.
So I don't know, stupid.
You know where do quasi-Fuchsian groups get their? You might wonder how do they accumulate their Hausdorff dimension? It might be the kind of curly Q nature of it. Like it's trying to be kind of two-dimensional. Whereas this is sort of extremely spiky, and so it's possible that it could be one-dimensional because it's so spiky.
So if S and T are close to 0, this becomes close to 1.
It becomes close to a line. Although you can rescale it. You can kind of renormalize it, and then you'll get some deformation which is given by our cocycle on the modular group. Something. So that might be the kind of let S and T go to 0 and rescale it, and this gives you some simpler thing, which is really the graph of a function.
So if we take the analogy of quasi-functional groups, I mean, you take any quasi-functional group, I mean, you deform it somehow, you know, and then you take the derivative of how points move off, and this gives you also transverse line fields. And so there are no, I mean, an invariant.
I see. So you take
There are a family of tangents, just because there are deformations. So you take a
Wait.
quasi-function, no? You take a quasi.
Okay, you take a quasi-Fuchsian group.
Yeah, and now you deform it in the space.
Do you start with a Fuchsian one, or you take a quasi-Fuchsian?
No, I take a quasi-function one. I could start with function one. I deform it to be quasi-function to make my point. Now I deform, and now I take just an infinitesimal deformation. And then the way, you know, you can follow the way each point in the limit set moves off. And
You think you'll really get a differential?
Why
You
should
think
it
it,
be
differential.
transverse? Why should it be transverse?
yeah, this is,
This curve
yeah, this might be a really crazy.
Don't go in a wide, they'll move in a one-sided way. Do they?
I see, so
okay,
each,
good point. Yeah. Okay. So this is going to be full of zeros.
this might be a crazy, yeah, this might be a crazy
The
thing.
point, as I understood it, his point was that it's not a local thing. What you're talking is a local thing. Whereas his line field isn't going to come back to the curve on a global scale.
Right, but any other one
Well, that's
does.
another aspect of it.
It's an easy proof. Imagine there was a line field that two line fields that only intersected the curve once.
Yeah.
Now, you might as well just assume that, since these are both continuous, just assume you have a hyperbolic fixed point. Then you can apply, as you apply the hyperbolic similarity, it has unequal eigenvalues, and so it just squeezes this thing down and proves the curve is a straight line.
Right.
So that's the proof that if there's, the line field is unique, basically. So it's funny. I never did anything with this. I mean, I never knew what to make of this structure.
It's an interesting structure. It means the uniqueness of scale. I mean, uniqueness of taking orthogonals, right? I mean, there's only one way of,
Right, it's,
even though there's no tangent space. But there's uniqueness.
right, the curve has this,
tangent space.
it's the dual to a line field, which is uniquely transverse to it. Yeah. Well, I always,
When you speak of hitching components,
Mhm.
so these are really components whose dimension is the dimension of the whole representation space.
Mhm.
Whereas the space of representations of modular group in PGL3,
it's large, yeah, so I think, yeah, so it's large, these
It's
are,
not a component.
yeah, so I think one of Kapovich's students, maybe it was this guy, but I think that he found another dimensions worth of cusp preserving ones that were also act properly. This is, I don't know this word too well, but yeah, there's more. You could try to count dimensions. Like one thing that's nice about these is that they're parabolic respecting. You would want that.
right?
But then even so, I mean, the dimension, right, I mean, you have Z3 mod, free Z2 just with this one other equation. So probably, yeah, there's more.
Mhm.
These seem especially nice. But I can't remember the properties of these other ones that Kapovic is. I don't think they're quite as good. Yeah. Okay, well, I hope that makes sense.